So I'm going to be talking about a project I've been working on for about a year or so, which is about estimating multivariate probit models. So just to give some background, so usually in medicine we estimate test accuracy by assuming that there's a gold standard test, which is assumed to be like 100% accurate. And to relax this assumption, you can use latent class models, but they assume that the test results are uncorrelated, conditional on the disease status, so whether they're positive or negative. But that's not really realistic. And they are computationally very cheap, which is good. And they can be extended to model that dependence, but that makes the identifiability problem worse because you've got too many parameters to estimate, especially if you've got just two tests. Without very strong priors or fixing parameters, which is often done, but probably shouldn't be done. You can also extend it to meta-analysis, where identifiability becomes less of an issue. Or multiple population models, which are basically just meta-analysis models, but with complete pooling or fixed effects, or whatever you want to call it. And they do have important drawbacks though, like they can't be extended to model ordinal tests without dichotomizing the data, or 3 or more tests, which is often you have many tests. And for the meta-analysis, it's really difficult to partially pool the conditional dependence parameters. So a model which addresses these issues is the multivariate probit model, a latent class version of it. This basically works by introducing a latent variable, z, on the observed data y, which is truncated at 0. And that depends on the observed data. So if it's less than 0, it's negative. It's greater than 0, it's 1 or positive. And then you apply a multivariate regression model to that latent data. And we applied this model, or the meta-analysis version of it anyway, using Stan in our previous work. And we reanalyzed a data set looking at tests for deep vein thrombosis. So there was one ordinal test with 3 categories, the Wells score, and 2 binary tests, so ultrasound, which the original meta-analysis assumed to be perfect, and the blood test called D-dimer. And we found that making the assumption of conditional independence or a perfect gold standard, or both, could bias a lot of the accuracy estimates, especially the joint test accuracy. So if you did, the D-dimer followed by the Wells score, especially the specificity. But that increased flexibility comes at a price, so it's very computationally expensive. So another way of parameterizing the model is to use the GHK algorithm or parameterization. So this expresses the truncated normal parameter z in terms of uniform parameters u star. And this was implemented in Stan first by Ben Goodrich, I think, as far as I know, a few years ago. And that's how it works. But basically, the point of doing that is that it's easier on the sampler because you're sampling from variables which should be uncorrelated, or at least much less correlated to each other. So you don't need a massive mass matrix a dense mass matrix to get good efficiency from it. So in terms of what we did, so simulate data, fix some stability issues, overflow and underflow, put it in an R package called Bayes MVP, and then compared the efficiency of 3 software, so Stan, M+, and the R package. So for the data simulation and priors, so the simulated data was motivated by viral and infectious diseases, because that's just what these models are used for a lot, although they should be used for other areas more as well. And there was 5 tests, so a dimension of 5. N varied from 500 to 25,000. The number of observations is 5 times more than that, though, so there's quite a lot of observations in the largest data set. The disease prevalence was estimated to be 20%. And for the correlations, we assumed a strong correlation in the disease group, so double or strong, and the matrix is very uneven, so 0 to 0.7, but all positive. And the priors weren't all like non-informative, or there's no such thing as that anyway, really, but they're mostly got some information in there, except for the test 2 to 5, sensitivity and specificity. Those aren't ideal priors necessarily, but yeah, that's just what we use, because that reflects kind of what people do, although people often don't put any prior information in, but yeah. So for the stability, so a problem with the model is that there's a lot of like underflow and overflow issues, and this parameterization is the one that Ben Goodrich first implemented, and it uses stands built in, Cholesky correlation parameterization. Although this is better, I think, than just declaring it as a correlation matrix in the parameters block rather than a Cholesky factor of correlation matrix. You still get divergences, especially for low n, and that's because, well, the latent class aspect exacerbates that problem, because in the smaller latent class you've only got like 100 people, even though n is 500. So, yeah. So using Sean's parameterization, which he talked about this morning, it greatly improves that issue, especially for like larger n, and pretty much goes to 0, but then there's still some divergences, and that's just, again, because of the latent class aspect. If it wasn't latent class, it wouldn't really be an issue in this case, unless n was like really small. So first thing I did, not really the first, I'm presenting it that way, but whatever. I did this more recently, but I vectorized the GHK parameterization, which wasn't that obvious how to do it, because every observation relies on the previous one. But if you like use block matrix operations and stuff, you can do it in Stan, at least partially, like column by column. So each column is vectorized, not the whole thing. And this makes it quite a bit faster. Not dramatically, but sort of between 30 and 80-ish%. Doesn't improve divergence issue, obviously, because it's still like the same model. Working on the log scale does, though. So if you, with the log likelihood function, you can just work on the log scale as much as possible. For example, using the standard normal log QF function, which inputs the log probability rather than the probability, like using phi or phi approx does, CDF of standard normal. And your output's still on the probability level. So the blue line is like that model, so it's much lower divergences, but less efficiency, because there's more computation. I eliminated the divergences completely by using inverse phi approx function and phi approx, which is I found on a very obscure forum about HP calculators. Yeah, I don't know why it was, yeah, but it's really weird to reference it, but yeah, and it works really well. It matches the phi approx function like exactly, so it's like like really good inverse for it, and it's very stable. But it doesn't improve the efficiency issue because it uses sin h and a sin h, so there's 2 logs and 1 exp in it, so it's got a lot of computation. So what you can do is work on both log scale and probability scale. So before I introduced the GHK parameterization, so you got like the latent variable capital Z, then you got the lowercase z, which is the standard normal, but truncated. That has a bound, so if you get the bound of that, and you can, put whatever boundary you want. So I use plus and minus 5. So if it's greater than the absolute value is greater than 5, it works on log scale, otherwise it works on probability scale. The majority of the time, it won't be that extreme in the tails. So there won't be that much computation overall. It's like you get the best of both worlds. So no divergences and really good efficiency, or at least matches pretty much the probability scale efficiency. So to summarize the R package, there's both computational and algorithmic aspects of it. I'm just going to go through them now. So for the mass matrix, I used a partially dense one. So a dense mass matrix for the correlations and coefficients, for example, and disease prevalence. And then for the nuisance parameters, or the U's, I introduced previously. It's diagonal, which is like what Stan does. For the burn-in, I use between chain adaptation, which this is based on an algorithm on a paper called Snaper HMC. And basically, rather than just looking at the mass matrix and step size and path length and things like that, the HMC parameters within each chain, you also look at it between the chains. So every 25 iterations or whatever you want, you can do every iteration if you want, you sort of average them out, and it makes the burn-in more effective and more efficient usually. I'm just going to go over vectorization or single instruction multiple data programs. So in Stan, you can do this by, like if you're multiplying two vectors, vec x and vec y, you can do this by putting a full stop before the asterisk, as far as I know. And it performs x operations simultaneously rather than one at a time, like a loop. And it would depend on your CPU and things like that, but how many it does. So in C++, if you're using eigen, which is what Stan uses behind the scenes, you can do it by putting a dot array after the vectors. And then that will do it element-wise for you. Or you can do it manually, which you only want to do if you really have to, because it's really annoying. Or maybe not annoying, but it's very tedious. So like just to do a multiplication, if you look at the bottom right, the green code, you have to use the functions that match the vectorization type. So if it's AVX512, for example, that's 512-bit, you need to use that stuff. And then if you want to use another one, you need to change the code. And that's not all the code, that's only a little part of it. You need to also do other stuff. Because that's each subvector, which has got 8 numbers in it. And then you need to loop around that if you want to do the whole vector. But that's what happens behind the scenes in like Stan or eigen library or whatever, as far as I know. It also uses chunking, so it splits, rather than putting the full container or vectors or matrices into memory, you split them up and then you do the vectorization on each chunk. And you can see the results of that here. So on the HPC and laptop, so if you just look at the HPC on the left, you can see that the ideal scaling is the dotted lines, and it gets closer when you do the optimal number of chunks, which is the blue line. So if you go from 32 to 64 cores, the computer's got loads of cores, obviously. It scales much better. Whereas if you don't do that, there's no point using more than 32 cores. You're just wasting the computer. Like it's just wasting 2/3 of it, because it's got 96 cores in total. But and on the laptop, it's a similar story. So this doesn't just apply to HPCs. There's no point going above like 4 cores if you don't do that. In this case, anyway, for this model. For the fast functions, so I found these on Stack Exchange, and these were for floats, which are 32-bit. Stan uses doubles. I did that as well, otherwise the algorithm doesn't work properly. And these are about twice as fast, but very accurate still. So yeah, the percentage error, it's like tiny, so they work very well. And yeah, this is just a bit more on the specs. So the laptop, the main difference is basically it's got double the cache per core and up to double the vectorization speed, because it uses AVX512 as opposed to AVX2. And it won't need to go out to RAM as much, which is slower. So compared to Stan, it's much more efficient, but this isn't really surprising. It's not a fair comparison, because Stan's general, whereas this is specific. But yeah, and you can see those gains are not just computational. So it's the ESS per grad is higher because of the algorithmic stuff. Compared to M+, which is a more relevant competitor, it's still much more efficient, so like 10 to 50 times more, and then for the laptop, 4 to 12 times more. And it's also more flexible. Stan was essential for development Bayes MVP, because I use it to do the priors and Jacobian adjustments. And there's no point coding those manually, because you don't really get a gain from it, as well as many other reasons why it was important. Other things we tried include GPU programming, Lagrangian Monte Carlo, and within-chain parallelization. I only briefly attempted these things. They didn't work. I do want to revisit GPU programming because I think using the more inefficient parameterization will actually be more efficient for this model, because even though it's less efficient in terms of ESS per grad, the GPU benefits might outweigh it, because you can write it as a product of like big matrix multiplications, which I think GPUs are meant to be good for. and with in-chain parallelization. I only tried it with OpenMP. So this is just the conclusion slide. So yeah, so to summarize, I vectorized the GHK MVP stan. In terms of time saved for 2,500 people, it's like an hour versus 5 minutes compared to N+. HPC, 20 minutes versus 40 seconds. For really big data sets, you also get big savings. 3 hours versus 9 minutes on the computer, for example. Yeah. And this will make it possible to perform like simulation studies and analyze large data sets and things like that. And on the right is just things that I want to do as well. And yeah, kind of in terms of the bottom Stan, this is my question I have, I think, actually. Yeah, so whether that could be implemented into Stan, if it's more formalized, and yeah, like with the approximations and things like that. So, yeah, thanks for listening. Yeah.
Yes is the answer to your last question.
Oh, no, okay, nice.
We can put analytic gradients in the C++ library. We don't just auto-diff through the low-level functions.
Yeah.
So we should do this.
Cool. Yeah, because if I could, like, if I could have just done it all in Stan, that would have been a lot better. Or most of it, anyway. Yeah.
Should talk to Ben. He'll do this.
Cool.
Or you.
There's no other questions, is there? I don't think.
Any other questions? Thank you.
Cool.